Greetings, calculus students. The topic for today is a process called implicit differentiation. Usually, when a function is defined, we have an explicit formula for it, something like f of x equals x squared plus e to the x. And there's one variable. But other times, a function can be defined indirectly through an equation that involves two or more variables. For example, x squared plus y squared equals 1 indirectly defines y as a function of x, or we say y is implicitly defined as a function of x in that equation, because maybe we could solve that equation for y in terms of x. But usually solving for y in terms of x is a difficult process. What implicit differentiation allows us to do is to extract the derivative dy dx from that equation without first solving that equation for y in terms of x, which is sometimes even impossible. So today we're going to learn that process.
Hello again, calculus students. Today's topic is implicit differentiation. So implicit differentiation is a really cool process for calculating derivatives, and it applies to equations. Let me try to tell you what I mean by that, because you're probably thinking, well, we've been doing equations all along, like f of x equals x squared, things like that. But we're talking about a different kind of equation here that can't necessarily easily or even at all be written as a function like f of x equals x squared plus 4 or something along those lines. So we might have some complicated equation like, say, x squared plus y squared equals 1. Or maybe even something way more horrible like the second one here. This is sort of a subtle point that I'm getting ready to make. When you have an equation that relates two variables x and y, then you can think of the variables as depending on each other because of that equation. In other words, you can think of, say, the value of y depends on the value of x in that equation, because in that equation, if I were to plug in a particular value of x, then that would determine a value of y. I could solve for the value of y that would satisfy the equation. So for example, in x squared plus y squared equals 1, if for whatever reason we put in the value of x equals 1/2, then we could take that x equals 1/2 and substitute it into the equation, and we'd have 1/2 squared plus y squared equals 1. And from there, we could subtract 1/4 from both sides, and we'd end up with y squared equals 3/4. And then you could solve for y by taking the square root of both sides, and you get y would be plus or minus the square root of 3/2. So you see, by substituting a value of x, it indirectly determines a value of y, and if you're able to, maybe you can solve for that value of y. But even if I did the same thing in that second equation up there, if I substituted x equals 1/2 in for x, in principle, I could solve for y and determine what values of y would satisfy the equation after you put in x equals 1/2. So in other words, the value of y would depend on 1/2. So in these equations, we understand that each variable is implicitly defined as a function of the other variable. So that's kind of it's a subtle point. Let me repeat it. In equations involving two variables, x and y, like we have at the top of the screen there, substituting a value of x determines a value of y that would satisfy that equation. That means that each of those equations defines y implicitly as a function of x. So whenever a function is defined implicitly, you may not be able to actually get your hands on what that formula for the function would be. All you know is that y is a function of x, but you don't know what the formula for it is. So that presents us with a little bit of a difficulty. What if I need to know what the derivative of y is? Well, turns out there's enough information from the equation that we can deduce what the derivative of y would be in terms of x. Let's go with this theme a little bit. So in this equation, x squared plus y squared equals 1. We understand on some level right now that y can be thought of as a function of x. If I put in a value of x, it's going to determine what the value of y is. So I can think, okay, y is a whole function of x. I don't know what the explicit formula for it is. So then if we're thinking of y as being a function of x, then that equation, x squared plus y squared x squared plus y squared equals 1 becomes something, it's the same thing still, but we're going to view it in a slightly different way. It becomes x squared plus y of x, thinking of y as an entire function. Y of x squared equals 1. All right? So this is subtle, but at this point, there's some mystery function that y is. I just don't know what it is. And then, but I can think of it that way. And now, what I could do is take that equation in blue and differentiate both sides with respect to the variable x. So I could take the derivative with respect to x of both sides. And the derivatives would have to be equal. If two things are equal, then their derivatives are, of course, equal. So all I'm doing here is taking the equation that's highlighted in blue up there. That should be y of x squared. But we're just taking that equation in blue and differentiating both sides with respect to x, and we can do that because, two things that are equal have equal derivatives. Now, how would we go about computing that derivative? Now, the thing is, we're differentiating with respect to x. So x is the independent variable. And so I can use my derivative rules just like usual. On the left-hand side, I'm taking the derivative of a sum, so I'm just going to write that as the sum of the two separate derivatives. Of course, the derivative of 1 on the right-hand side is just 0. And now let's look at that left-hand side. What's the derivative of x squared with respect to x? Well, that's just the sort of thing we've been doing all along. That's just 2x. But the next part's where it's interesting. What is the derivative of y of x squared? Well, how would you take the derivative of just any old function, f of x, if the whole thing was squared? Well, this is a situation where you'd use the chain rule. The chain rule says if you want to take the derivative of a whole function squared, you can bring that 2 down, and then you'd have f of x just to the first power. But then, because it wasn't just a variable being squared, it was a whole function squared, you got to multiply times the derivative of the inside function, right? So I'm going to do exactly that, except instead I have f of x, I have y of x. So when I differentiate y of x squared, it's going to be 2 times y of x times the derivative of y of x, so just dy dx. Or I could have just put y prime there, either way. And then that's equal to 0. So at this point, I've got an equation, and in that equation, I see dy dx sitting there. And so the idea now is we can algebraically solve for dy dx. So that's my next step. Solve for dy dx. And I would arrive at, I would subtract 2x from both sides and then divide both sides by 2 times y of x. So I would get dy dx equals negative 2x over 2 times y of x. And I'm going to cancel the 2's off. So I have negative x in the numerator. And in the denominator, instead of writing y of x, I'm just going to write y. Well, we understand y is a function of x, but check it out. We just calculated the derivative of y with respect to x. It turned out to be negative x over y. Notice that the derivative has 2 variables in it, but that's not surprising because the equation that we started with, x squared plus y squared equals 1, had 2 variables in it. So this is typical. So the trick was to just think of y as a function of x and treat it like a function, give it that kind of respect so that whenever you go to differentiating it, maybe it's raised to a power or something like that, you use the chain rule when you differentiate it. So we just found dy dx equals negative x over y. So the process I just showed you is what we call implicit differentiation. So all this that we were doing here was the process of implicit differentiation. Don't worry, we're going to do lots more of it. We're going to do lots more of it so that you have plenty of practice and get a better feel for it. Now, before we go to doing a bunch of examples, though, I just want you to be a little bit convinced that this sort of makes some sense. Like, one thing that we could do to verify that our answer for dy dx is actually correct is we could go back to the original equation and do it a different way. So we started with x squared plus y squared equals 1. Now in this equation, it's a pretty simple equation involving 2 variables. I could actually solve for y if I wanted to. And if I solved for y, I'd have y squared equals 1 minus x squared, and then I would have to take the square root of both sides, and I'd get y is equal to plus and minus the square root of 1 minus x squared. you may recognize that that original equation was a unit circle, right? It's this circle of radius 1 centered at the origin. So what we did by solving for y was we found the equations for both the top half and the bottom half of the unit circle. This top half of the circle is your y equals the positive square root of 1 minus x squared. And that's a function, right? It passes the vertical line test. And then we have the bottom half of the circle here. This would be the negative root. Y equals negative the square root of 1 minus x squared. So that's what we're seeing algebraically. The y being plus and minus the square root of 1 minus x squared is just the top and bottom half of the circle. But now let's take the top half of the circle. So I got y equals the square root of 1 minus x squared, because I need a function if I'm going to use the rules that I know from before. I can't have both the plus and the minus going at the same time. And then I want to calculate the derivative. So what's dy dx? Well, we just recently learned about the chain rule, and we understand that, that square root of 1 minus x squared is really 1 minus x squared to the all to the 1/2 power. So I can apply the power rule along with the chain rule to this, and I would get 1/2 1 minus x squared, and then I would subtract 1 from the exponent and get negative 1/2. And then the chain rule says I got to multiply times the derivative of that inside function. So there's negative 2x as the derivative of the inside. And let me simplify just a little bit. Notice that the 1/2 and the 2 cancel one another. And the fact that that's a negative exponent there, I can put it down in the denominator. So I've got negative x in the numerator, and I've got this 1 minus x squared to the 1/2 in the bottom, in the denominator. So that's negative x over square root of 1 minus x squared in the bottom. And finally, just for a last little step, notice that y is equal to the square root of 1 minus x squared. So if I were so inclined, I could substitute y in for the denominator here, and I have negative x over y. That's exactly what we got for the derivative doing that implicit differentiation process. And we would get exactly the same result if we did it for the other half of the circle. If y is negative the square root of 1 minus x squared, that's negative 1 minus x squared to the 1/2. Differentiating it is almost identical except for the minus sign, right? So I'm going to bring the 1/2, I have a negative, I bring the 1/2 down, 1 minus x squared to the negative 1/2 times negative 2x. This time the negative 1/2 cancels with the negative 2, and I just have positive x in the numerator, and then I have 1 minus x squared to the 1/2 in the denominator, and then I can write that as x over, but if y is equal to negative that radical, then what you see in the denominator there is negative y. But notice that those answers match, right? So it didn't matter which half of that circle we were doing, we got the same derivative. So the point of this was just giving you some confidence that that sneaky process that we did a minute ago gets the same result, what we did at the bottom of the screen here. And then, yeah, if you can solve for y and get y as a function of x, sure, you could go ahead and just differentiate it the old-fashioned way. But I challenge you, say in the second yellow equation there, the really complicated one involving cube root of y squared minus 7, that big thing. Like, you just aren't going to solve that for y in terms of x and then differentiate it that way. You just can't explicitly solve for y. So you can see where this implicit differentiation process is handy, because it doesn't require you to have to solve an equation for y in terms of x, which may be impossible. So let me give you the implicit differentiation process in a nutshell. What you're going to be given to start with is some equation that involves two variables, x and y. We're going to stick with x and y for now, but a little later we might have an equation with different variables, but you would modify the process accordingly for the different, what the different variables' names are. And then what we want to find from that equation is the derivative of y with respect to x. In that equation, as we discussed, we can kind of think of y as a function of x. So that's step one. Just in your mind, this is more of a mental step than anything. Just start thinking, okay, y, you're not just a letter, you're not just a variable, you're an entire function of x. And then, once you have that in your mind, you differentiate both sides of the equation that you were given with respect to x. So you take d dx of both sides of the equation. 3, as you're differentiating both sides of that equation, anytime you run across the y, you got to remember, hey, y is a whole function of x, and use the chain rule appropriately. So when you use the chain rule on that term involving y, you're going to see the term dy dx, or y prime, pop out. And then the last step is simply to solve for the derivative that popped out from the differentiation process in step 3. So solve for dy dx. So step 4 is just an algebraic step of solving for dy dx, or y prime, whatever you're calling it. So let's see how this goes in practice. I'm going to find dy dx using implicit differentiation from the equation x plus 2y squared equals the square root of y. Mentally is okay, so I'm thinking y is some function of x, right? Y is some whole function. If it makes you happy, you can even think of something specific, like maybe it's 1 plus x squared or something weird like that. Think of y as being a whole function. You just don't know what that function is, because in order to find what that function is, you'd have to solve the original equation for y in terms of x, which may be difficult or impossible to do. But get that in your mind. Y is some function, some f of x. Okay, now the process is to take the derivative of both sides of the equation. So let's just write down that we're taking the derivative of both sides. All right. Now on the left-hand side, I'm going to break it up as taking the derivative of the two separate pieces, just to be documenting very carefully what I'm doing here. Now, let's do those derivatives. Well, the first derivative that just involves x, we just differentiate like usual. If the term that you're differentiating only involves x's, you just differentiate like you always would. So d dx of x is 1. And now we come to, we're taking the derivative of something that involves y. Now off to the side here, what I'm thinking of in my mind is I'm not just differentiating the letter y, I'm differentiating 2 times some whole function squared. And if I was going to differentiate that, I'd pull the 2 out, then I'd bring the 2 down, that's the exponent, then I would do f of x, and I would lower the exponent to the first power, and then I'd have to use the chain rule and multiply times the derivative of the inside, right? So I'm going to do exactly that, but instead of calling it f of x, I'm going to call it y. So what I would end up with is pull the 2 out, then I get the derivative of y squared is 2y, but then I got to use the chain rule and multiply times dy dx, or y prime, whatever you want to call it. Okay, so a dy dx popped out. Great. That's the sort of thing that you're expecting to see when you differentiate terms involving y. And now the similar sort of thing on the right-hand side, if I were taking the derivative of the square root of some whole function, well, that's the same thing as differentiating that function f of x to the 1/2 power. And so I would bring the 1/2 down, and then the exponent would get reduced to the negative 1/2. But then, because there's a function inside that radical, I got to multiply times its derivative using the chain rule. So again, I'm going to do exactly the same thing with the square root of y, treating it as a function. So up here I would get, bring the 1/2 down, then I'd get y to the negative 1/2. Then I got to multiply times the derivative of the inside function, which was y. So I multiply times dy dx. So implicit differentiation is really just thinking of something as a function and using the chain rule. So it's really just sort of a special case of using the chain rule. Now, in this equation, I've got a couple of dy dx terms, and my job now is to algebraically solve for it. So typically what you do here is you gather all the terms that have dy dx on them on one side of the equation, move everything else that doesn't have a dy dx on it to the other side of the equation, and then you factor out the dy dx to solve for dy dx. So it'd go something like this. So I'm going to I've got this 4y dy dx, and I've got a minus 1/2 square root of y times dy dx. Then I'm moving over to the left-hand side of the equation. And the only term that doesn't have a dy dx multiplied times it on the left-hand side is that 1. So when I move it over, I've got negative 1. So it looks like that. And now I can factor the dy dx out. Now I have to urge a little bit of caution here. When you see this dy dx out here on the front of this, that is not telling you to compute the derivative of the stuff that's inside the parentheses. Dy dx is already a derivative computed, so you don't want to confuse that symbol with this symbol. This symbol means take the derivative, but when it's a dy dx, it's already a derivative taken. So it's it's a specific algebraic quantity. It's not an operation. So now I've got dy dx multiplied times this quantity 4y minus 1 over 2 squared of y equals negative 1. So I can just, to solve for dy dx, I just divide both sides by the stuff in parentheses, and I'd get negative 1 over 4y minus 1 over 2 squared of y. Though we could do some algebraic simplification of that, I'm not going to bother with it right now. So I'm going to put a box around it and say that's my answer. It may be helpful if I need to do something else with this derivative to simplify it a bit, but we're not doing anything else with it right now. We're just trying to find it. All right. So again, the process was step 1, think of y as a function of x. Step 2, differentiate both sides of the equation. Step 3, as you're differentiating, be sure you treat y as a whole function and use the chain rule, which results in some dy dx is popping up in your differentiation process. And then the last step is to simply solve for dy dx. Let's try another one. We've got tangent of x times y equals x plus y. And we want to find dy dx. This time we're specifying a point at the point 0, 0. Another way to write this, we could have written find dy dx. And we could put the vertical bar, and then we could put the ordered pair 0, 0 here. So first, I just want you to check that 0, 0 satisfies the equation. Because if we're going to compute the derivative at that point, the point that we're computing the derivative at needs to be a point that satisfies the equation. Well, that's pretty easy to check because, the point 0, 0 means your x is equal to 0 and your y is equal to 0, right? So substitute x equals 0 and y equals 0 into the original equation. You get tangent of 0 times 0 equals 0 plus 0. The left-hand side is just tangent of 0. Tangent of 0 is 0. And the right-hand side is 0 plus 0, which is, of course, 0. So this checks out, right? So the point that we were given does actually satisfy that equation. So now, let's start by taking the derivative of both sides of that equation. Now, in our minds, since we're finding the derivative of y with respect to x, we're thinking of y as a function, not just a variable. Think y as a whole function. Okay, so now, how do I differentiate the left-hand side? Well, you can see that it's a tangent function, and then it's got something more complicated on the inside. So that's a situation where you need to use the chain rule. So to use the chain rule on the left-hand side, I differentiate the outside function. Derivative of tangent is secant squared. And then you leave whatever's on the inside alone. And then you multiply times the derivative of the inside stuff. But I'm going to be a little bit more explicit and say d dx xy. So I'm taking the derivative of the inside stuff. So that's the chain rule. Now what do we have on the right-hand side? Well, the derivative of the first term, x, is just 1. And the derivative of y is the derivative of y. So I would just write derivative of y with respect to x. Okay. Now I still have another derivative in play that has to be computed before I can do the final step of solving for dy dx. I have to keep doing the process until I'm done taking derivatives. Now, how would you take the derivative of x times y? Well, x times y is kind of like doing x times some function f of x, right? And so if you're going to take the derivative of that, you got to use the product rule. So it'd be like x prime times f of x plus leave x alone, then you got to do f prime of x, right? So I'll do that same exact thing over here, but instead of f of x, I've got y, so that becomes, I'm going to take the derivative of the first term, which is 1, then I'm going to leave the second term alone, which is y, plus, then I'm going to leave the first term alone, which is x, and I'm going to multiply times the derivative of the second term. So the stuff that's in the parenthesis there I got from doing the product rule. Now I've got 1 plus dy dx on the right-hand side still. And now I have to solve for dy dx. So in doing that, I need to distribute the secant squared of x times y across these terms. So I'd get y times secant squared of xy plus, then I'll have x times secant squared of xy times dy dx. And now that equals 1 plus dy dx. And then underline in red the terms that have dy dx in them. So I want to gather those on one side of the equation and then move everything else to the other. So I'm going to gather my dy dx's on the left-hand side of the equation so that I'll have x times secant squared of xy times dy dx. Then I'll have a minus dy dx when I subtract the dy dx on the right-hand side of the equation from both sides. And then on the right-hand side, I'll have 1 minus y times secant squared of xy. So I moved everything that was not multiplied times dy dx to the other side of the equation. Now on the left-hand side, I factor out the dy dx. So I'll have dy dx multiplied times x secant squared of xy, and then minus 1. And that equals 1 minus y secant squared of xy. And now I divide by the quantity that's in parentheses on the left-hand side of the equation to isolate dy dx, and I end up with dy dx equals 1 minus y secant squared of xy, all divided by x secant squared of xy minus 1. And that is the derivative of x with respect, and the derivative of y with respect to x. We're not quite done yet because the original instructions asked us to find the derivative at 0, 0. So now that we know that the general formula for the derivative, I can calculate that derivative at a point, at the point 0, 0. In other words, this is just the derivative with respect to x, where x is equal to 0 and y is equal to 0. So that just means put x equals 0 and y equals 0 into the derivative formula. So I get 1 minus 0 times secant squared of 0 all over 0 secant squared of 0 minus 1. Well, you're multiplying 0 times the secant squared of 0, so in some ways you don't really even care what the value of secant squared of 0 is. I guess you need to be only worried about, is it defined? But yeah, secant squared of 0 is defined. It equals 1. So what you're doing there is 0 times 1. So you still get 0, so you get 1 minus 0 in the numerator and 0 minus 1 in the denominator. So that's a grand total of negative 1. And that's the answer we were after. Sometimes the algebra can get a little lengthy on these implicit differentiation problems, but it's usually not too bad if you're just neat and orderly about it and don't try to do too much at once. Just be careful. It amounts to good bookkeeping, and so you don't make a mistake somewhere along the way. But usually it's not especially tricky. It just can be a little long. And the algebraic expressions that you might get for the derivative might be kind of complicated. Now, I'd like to show you graphically a little bit what was going on in this problem. Whenever you have an equation involving two variables, you can graph that equation. And the graph of it will be some sort of curve. The curve, it won't be the graph of a function, though. Functions graphs pass this vertical line test. So typically, when you have an equation involving two variables, you'll find that it doesn't pass the vertical line test, but you get a curve. So let's see what happens on Desmos here if we punch in tangent of xy equals x plus y. Holy smokes, look at this graph. It's like not even just one curve, it's like a sort of a foliation of curves. And we were interested in what was happening at the point 0, 0, though, so let me zoom in around that point. So around that point, the curve looks like that. So there's the graph, and we found a second ago that the dy dx at the point 0, 0 came out to negative 1. Well, geometrically, what that means is that the slope of this tangent line is negative 1. And that looks right. When I just look at that tangent line, it looks like the slope is about negative 1. Our derivative is still doing the same thing it always did. It gives you the slope of a tangent line to a curve at a given point. But when you're dealing with an equation, it ends up being a bit more complicated. Okay, let's see another example along these lines. In the next example, we want to find the equation of the line tangent to the curve x cubed plus y cubed equals 2xy. And the point in question will be 1, 1 on the curve. Now, on the basis of our previous example, we know that what this is really coming down to is we got to find the slope of the tangent line to this curve at this point. So if we wanted to, just to see a picture of it, we could do that. So plugging it into Desmos, we saw we got this curve here, and the point in question is 1, 1, which is right there, that red point. And so we're looking for the slope of this tangent line that looks about like that. And I wouldn't be surprised if the slope came out to -1 just from the picture, just from the symmetry of it that it seems to have. But let's find out what the algebra tells us. So, but geometrically, we want to find m tan, right? The slope of this tangent line will be the derivative of y with respect to x at the point 1, 1. Now, after we have the tangent slope, we'll use the point slope formula to get the equation of the line as requested in the problem. Okay, so first step though is let's find dy dx. So we'll start by taking the original equation for the curve, and we'll differentiate both sides with respect to x. And we'll differentiate viewing y as a function of x. So got to get in the right headspace. Y is a function of x. Okay, so when I differentiate a term involving just x's, I just differentiate like normal. So I'd get 3x squared. Differentiating that y cubed, I'd get 3y squared, but then times y prime. If I could put there dy dx if I wanted to. I'm going to use y prime this time just because it's a little shorter to write. Okay, and then on the left-hand side, I'm computing a product, 2 times x times y. So I have to use the product rule. So I'm going to think of 2x as being the first factor in that product, and then y will be the second factor. So I'd get 2, the derivative of the first factor, times y left alone, plus, then I'll have 2x, the first factor, then I got to multiply times the derivative of y, which is just y prime. And now my job will be to solve for y prime. And there are my y primes in my equation I'm going to solve for. And I'll have 3y squared y prime minus 2x y prime on the left-hand side. On the right-hand side, I'll have 2y minus 3x squared. And then when I factor out the y prime and then divide by what was left, I get y prime equals 2y minus 3x squared divided by 3y squared minus 2x. Okay, so there's the derivative. And so from that derivative, I'm going to get my slope of my tangent line. It'll be y prime evaluated at the point 1, 1. So that just means put x equals 1 and put y equals 1 into the derivative formula. So I'll get 2 times 1 is 2, minus 3 times 1 squared is 3, over 3 times 1 squared is 3, minus 2 times 1 is 2. So that looks like -1 over 1, so it comes out to -1. That's kind of what I suspected it was going to be just from looking at the picture. It looked like a -1 slope. Great. Okay, so now I have my slope. So m tan equals -1, and I have my point on the curve is 1, 1. And so then I'm going to do the point slope formula and have y minus 1 equals -1 times x minus 1 is the equation of the tangent line. And if I like, I could solve for y, and I'd get y equals -x and then plus 2. So there's the equation of the tangent line. Well, I think you have enough examples to start working on your own and practicing. Hopefully the 4-step process I gave you will aid you in that effort. And I think I'll stop there. Talk to you next time.